Hello and welcome to today's lesson where we're going to look at some examination questions for the periodic motion topic of the AQA A-Level Physics specification, which is found on paper 1 of the course. So in the periodic motion topic we've covered the following topics: circular motion, centripetal forces, centripetal acceleration, simple harmonic motion, pendulums, the mass spring system, free and forced vibrations, resonance and damping. So in today's lesson we're going to look at the key ideas of periodic motion, prepare ourselves for assessments by looking at some questions and seeing how you answer these questions. So if we're successful and we learn in today's lesson, we can understand the different concepts of periodic motion, answer questions on periodic motion, and by the end you can review your understanding on periodic motion and look to how to improve on this further. So let's look at the first question here. So the mean radius of the Earth's orbit around the Sun is 1.5 times 10 to the 8 kilometers. What is the mean centripetal acceleration of the Earth about the Sun, where 1 year is 3.15 times 10 to the 7 seconds. So let's have a look at our answers there, and the correct solution is going to be answer B, because we're looking for centripetal acceleration. So you write out what your equation for centripetal acceleration is: omega squared r. Now we know omega is 2 pi f, so therefore we know 2 pi f squared, or 4 pi squared f squared, times by r is equal to centripetal acceleration. And at that point you can put the values in. Now whilst you're not given frequency in the question, you are given time period, which is 3.15 times 10 to the 7 seconds. So we say frequency is 1 over time period, which allows us to use that in the equation. We know what r is because it's the radius of the Earth's orbit around the Sun. We put our values in and we get 5.968 times 10 to the minus 3 radians per second squared. Right, the next question. This graph shows a variation of displacement x with time for an object performing simple harmonic motion, whilst large t is the period of the oscillation. So which graph shows a variation of acceleration with time for the object? Well, the answer is C, because we know acceleration is directly proportional to displacement. That is a condition of simple harmonic motion. So that tells us the shape of the graph should be the same. But the trick is, with simple harmonic motion, acceleration is directly proportional to displacement, but it's directly proportional to negative displacement. So whilst the x will be a positive, the acceleration will be a negative, and vice versa. So we're creating a reflection in the x-axis, which is our answer for C. Now, question 3. The graph shows a variation of velocity v with time t for an object performing simple harmonic motion. The period of oscillation is t. So the maximum acceleration of the object is equivalent to what? Right. Now the answer for this one is A, because the gradient of a velocity time graph, regardless if it's simple harmonic motion or any other type of motion, is equal to the gradient of the velocity time graph. So the acceleration is the gradient. Now the maximum value of acceleration will be when the gradient is the steepest, which we find to be at 0 from looking at the graph. So therefore that occurs, the maximum acceleration is the steepest gradient, which when t equals 0, so the answer is A. Next question. The total energy of an object that's performing simple harmonic motion is always what? Well, it's always going to be constant through a complete cycle, because there's two energy stores: the potential energy store, the kinetic energy store, and we assume that in simple harmonic motion, that whilst the energy can flow between the two stores, the overall total has to be the same. Now, just to clarify, the total energy can never be 0, as there's never no potential energy store. There's always some potential energy. The total energy is not a maximum or max speed, because the gravitational potential is a minimum at that point, and the total energy is not a maximum at maximum displacement, as the kinetic energy would be a minimum at that point. Right, question 5. The graph shows a variation of displacement x with time t for an object performing simple harmonic motion. Point P has a displacement of 2 centimeters from the equilibrium position. What is the velocity of the object at point P? So we've been given a displacement time graph. So what we can do with that is, therefore, we can use the equation V equals plus or minus omega times by a squared minus x squared. So you can then work out what the velocity is going to be at point P. Now, firstly, do we know what omega is? Well, omega is 2 pi f, and we know what the time period is because it's one complete cycle, which is 0.8 seconds. So 1 over time period is frequency, so 2 times by pi times by frequency gives us omega. Do we know what amplitude is? Well, it's going to be the maximum point on the graph, the furthest place from equilibrium, which is 3.9. And then we know what x is because that's what point P is, which is at 2. So you put your values in and you get 26.2 meters per second, which to a reasonable estimation is going to be answer C. Number 6. For a particle moving in a circle with uniform speed, which of the following statement is incorrect? Well, the incorrect statement is going to be C, because displacement always occurs perpendicular to the force, because the centripetal force always acts towards the center of a circle. The force is always perpendicular to the velocity, as is the centripetal force, and the kinetic energy is constant, as the magnitude of velocity never changes at uniform speed. Okay, but the velocity of the particle is not constant because the direction is always changing, and velocity is a speed and it's a direction. Right, a revolving mountaintop restaurant turns slowly, completing a full rotation in 50 minutes. A man sitting in the table in the restaurant, 15 meters from the axis of rotation. What is the speed of the man relative to a stationary point outside the restaurant? Well, what we do is we use the equation V equals omega r. Now, omega is going to be 2 pi over t, because it's 2 pi for one complete rotation and big T the time for that complete rotation. So we do 2 pi divided by 50 times by 60, because we work in seconds in physics. So we get to be 2.09 times 10 to the minus 3 radians per second. We then pop it into the equation V equals r omega. We know r is 15 from the question, so we get 3.14 times 10 to the minus 2 meters per second, which is pi over 100. So our answer is A. Next question. A particle of mass 0.2 kilograms moves with simple harmonic motion of amplitude 2.0 times 10 to the minus 2 meters. If the total energy of the particle is 4.0 times 10 to the minus 5 joules, what's the time period of the motion? Right, so we know the total energy is kinetic energy plus potential energy, which we can then work through with a couple of sums to equal a half Ka squared. So therefore total energy is going to equal a half times by mass times by angular velocity squared times by acceleration squared. So we rearrange that and work it through. So we work it out to be equal to the omega squared equals 2. So therefore omega equals 1. So therefore 1 equals 2 pi over t. So t is 2 pi over omega, which is 2 pi over 1, which is equal to 2 pi. So the answer is D. Number 9. This graph shows a variation in displacement with time for an object moving with simple harmonic motion. What is the maximum acceleration of the object? Right, so how can we work out the maximum acceleration of the object? Well, you can't use the gradient in this graph because it's not a velocity time graph, it's a displacement time graph. So we're going to have to use the equation instead. So we have to use the equation maximum acceleration equals omega squared a. Now we know omega is 2 pi f, and from the graph we know what f is because we know f is 1 over time period. And the time period for this graph is 2 seconds because that's the time it takes before it repeats itself. So we work out frequency is 1 over 2. We work out omega squared by using 2 pi f all squared. And you times by the amplitude, which is the maximum possible displacement from the equilibrium, which is 10 times by 10 to the minus 2 meters. Now don't forget that there's a 10 to the minus 2 in the heading of the units there, so you're going to have to include that. So our answer is 0.99 meters per second squared. So the answer is B. Question 10. A simple pendulum and a mass spring system are taken to the moon, where the gravitational field strength is less than on Earth. Which line, A, B, C, or D, is the table that correctly describes, if any, in the period when compared with the value on Earth? So on the moon, the gravitational field strength will change, which only affects the pendulum and not the mass spring, because G is only in the time period equation for a pendulum, not the mass spring system. So because we know it's 2 pi times by the square root of L over G. So what that means is if G is getting smaller, the time period value is getting larger. And in addition, you know, because the restoring force is smaller, so it's going to take longer to get back to equilibrium and then continue on with inertia. So whilst for the period of the pendulum, it will go up, the time period of the mass spring will not change because G is not in that equation. So the answer is A. Question 11. Two pendulums P and Q are set up alongside each other. The period of P is 1.9 seconds and the period of Q is 1.95 seconds. How many oscillations are made by pendulum Q between two consecutive instants when P and Q move in phase with each other? Now, the answer is B, and let's have a look at this. The frequency of P is 1 over time period, so it's 1 over 1.90. The frequency of Q is 1 over time period, so it's 1 over 1.95. So the difference in frequency is therefore the difference in these two values, which is 0.013 Hz. So the time interval of the frequency being in phase again is going to be 1 over this change in frequency. So its time is 1 over 0.013. So the time it takes before the back in phase again is 74 seconds. But for Q, one oscillation takes 1.95 seconds. So to work out how many oscillations Q makes in these 75 seconds, you do 75 over 1.95, and our answer is 38. So the answer is B. Right, the diagram here shows a 12-hour analog clock. What's the average angular speed of the hour hand? Well, we know that angular speed, omega, is 2 pi over t, so it's 2 pi over the time it takes to go around the clock once, which is 12 times by 60 times by 60, because we work in seconds in physics. Remember, it goes around the 12-hour clock, not 24. Okay, so you work it through to be 1.45 times 10 to the minus 4 radians per second. Question 13. A car of mass of 1,200 kilograms travels at a constant speed around a horizontal circular bend of radius 15 meters. The car travels from P to Q in 1.8 seconds. What's the centripetal force acting on the car? Right, we know that we can work out omega, because omega is the change in angle over the change in time. Now we know the change in angle because it's 90 degrees, but we work in radians. If I'm looking at the diagram, it's going to be pi over 2. So you do pi over 2 divided by the time, which tells you in the question is 1.8 seconds. So our angular velocity is 0.87 radians per second. So we then can use the centripetal force equation, F equals m omega squared r. We know what m is in the question, 1,200 kilograms. We've worked out omega, and we can multiply it by r, which is given in the question 15. So we get an answer of 13,707 newtons, which rounded about correctly is 14,000 newtons. The answer is B. Question 14. The diagram shows two connected wheels, X and Y. The diameter of wheel Y is twice the diameter of wheel X. Wheel X drives wheel Y with the belt. The belt doesn't slip. X rotates at a constant rate. So what's the ratio of the angular speeds of X divided by Y? So if you think about it, angular speed is equal to V over R, because we know V equals R omega. So omega is V over R. So if X is driving Y, they've got to have the same velocity because they're driving each other. So therefore, V is the same. But if Y has double the diameter and therefore double the radius, by looking at this equation, it's going to have half the angular speed. This means X has double the angular speed of Y, so it's going to be 2 to 1. The answer is B. Question 15. A ball of mass 0.2 kilograms moves in a horizontal circle of radius 50 centimeters at the end of a string. The ball moves at a constant speed of 9 meters per second. What's the horizontal force exerted by the ball on the string? So when we look at this example, it's going towards the center of the circle because it's the horizontal force which is acting as the centripetal force. So the string will pull the ball towards the center, and therefore Newton's third law, the string will pull the ball away from the center. So our answer in this case is actually going to be from the centre, because we're not looking at the actual centripetal force, we're looking at this Newton's third law pair. But we need to work out the size of this Newton's third law force, so we can, because it's equal but opposite in direction, we can use the centripetal force equation to work out its magnitude. So F equals mv squared over r. So what is m? 0.2. What is v? 9 from the question. What is r? 0.5, because the radius is 50 centimeters, so we work in meters in physics, so you get 32.4 newtons, and remember it's acting away from the center because it's the Newton third law pair, not the actual centripetal force. Right, question 16. This graph shows a variation of velocity v with time t for an object undergoing simple harmonic motion. What's the amplitude of this motion? Now again, you can't actually use the graph to identify it because the graph is a velocity time graph. So you're going to have to use the equation maximum velocity equals omega a. And remember, omega is 2 pi f. So let's rearrange that to make a the amplitude, the subject. So we do v over 2 pi f. Now we know what v max is from the graph because it's shown it's the highest value possible, so it's 2. And therefore you go 2 divided by 2 pi f. Now what's f? Well, f is 1 over t. We know from the graph that t is the time it takes to repeat, so it's 1.60 seconds on the graph. So you put all those values in and we get a equals 0.51 meters. The answer is D. Question 17. A mass spring system of mass m oscillates with a frequency f on a spring with spring constant k. A second mass spring system oscillates at frequency 3f. Which row is correct for the second system? Right, let's think about this logically. If t equals 2 pi times by the square root of m over k, well, f is going to be 1 over this because f is 1 over t. Now, for f to be 3 times bigger than m over k, it's got to be 9 times smaller because it's actually f squared is equal to m over k from the equation, because f is equal to 1 over, fundamentally, square root m over k, because you take off the constants. Okay, so therefore, it's got to be squared as the denominator. So therefore, you've got to look at the combination given where you'll get 1/9. Now, 18 over 2 isn't 1/9, it's 9. 9 over 3 is 3. 3 over 9 is a third, but 2 over 18 is a ninth. So therefore, the answer is D. Question 18. The variation of displacement x with time t for an oscillator of mass m is given with x equals 2.4 cos times by 0.76 t. What's the total energy for the oscillator? So like we mentioned before, the total energy in an oscillator is kinetic energy plus potential energy, which when you work it through, because you can work out the value for the kinetic energy by doing a half mv squared, but then subbing in the values, and the same for potential energy, mgh was subbing in the values. So when we sub in all the values, our total energy for an oscillator is a half times by mass times by angular velocity squared times by acceleration squared. So what you do is you pop in all the values that you know, and then you work out your answer to be 1.66 meters, or the answer is C. Question 19. A mass on the end of a spring oscillates with simple harmonic motion with a frequency of 2.7 Hz. The distance between the top and the bottom of the oscillation is 12 centimeters. What's the maximum speed of the mass? Right. So again, it's simple harmonic motion, and whilst it's a mass spring system, so you might be tempted to use the mass spring equation, you can just use a general simple harmonic motion equation for this one. So the maximum speed, or V max, is equal to omega A, where omega is 2 pi f. We know what f is, it's 2.7 Hz. We know what A is. Now be very careful here, because amplitude is from the middle point, the equilibrium position, to top or bottom. So if the distance from top to bottom is 12, the amplitude is actually 6. And we don't work in centimeters in physics, we work in meters. So as a result, we use 0.06 meters as our amplitude, and we get an answer to be 1.01 meters per second. Question 20. Centripetal acceleration is always directed where? Well, centripetal means towards the center of the motion, towards the center of the circle. So the answer is always C. Now remember, centripetal force acts towards the center of a circle, and centripetal acceleration acts towards the center of a circle. Okay, centripetal means it goes towards the center of the circle. Right, a body of mass m oscillates with simple harmonic motion on a spring constant k. In one instance in the oscillation, the mass is a distance y above the equilibrium position, which rho gives the magnitude and direction of the acceleration of the mass. Right, so acceleration is equal to F over m. Now we also know from Hooke's law that we know that F equals kx. So we can put that in. Now remember, we can therefore link it into the actual equation. Now remember, it says the mass m is a distance y above the equilibrium position. So instead of using the notation x for extension, we're using the donation y, which might look a bit confusing, because you might have seen previously that f equals kx, but in that first line it says f equals ky, which is exactly the same. It just is in the question told you that we're using y for extension and not x. So therefore, acceleration is ky over m, so it has to be either A or B, but remember, acceleration always acts towards the equilibrium position, which is always, in this instance, back down, okay, so as a result, it must be acting downwards. Now, in question 22, a simple pendulum oscillates with a frequency of 0.5 Hz. Which pair of graphs show the variation with time of its potential energy and its kinetic energy? Right, firstly, remember, energy is a scalar, so you can never have a negative energy. So straight away, any graph which shows a negative energy is always going to be wrong. Now the energy stores change between maximum and minimum every half a cycle, which in this instance is 1 second, because as we know the frequency is 0.5 Hz, the time period, which is 1 over 0.5 Hz, is equal to 2 seconds. So when you look at these particular examples, when do you get a change in kinetic energy and potential energy oscillating between maximum and minimum every 1 second? Well, the answer is C. Right, this graph shows a variation of amplitude with frequency for a forced oscillation of a lightly damped system. P marks the maximum amplitude of the system. Now the damping on the oscillator is decreased, and each of the following graphs is drawn to the same scales as the scales of the graph above. Which graph shows the new variation of amplitude with frequency? Now, let's think about this logically. When you have dampening, what does dampening do to the peak of resonance? Well, it dulls it. So it doesn't make the point isn't as high, the increase isn't as sharp, so it's flatter, and it's slightly shifted to the left to a lower frequency. But this is actually asking for the inverse. What would happen if the dampening wasn't increased, but it was decreased? So therefore, it would shift slightly to the right, it will be more pointed and sharper, and it will be higher. The only one that satisfies all three is answer A. 24. A simple pendulum oscillates with the same time period as a mass on a spring. Which rho gives a combination of pendulum length, mass, and spring constant that produce the same time period in each system? Assume G is 10 newtons per kilogram. So remember, we know that time period is approximately 1 over the square root of m over k, or 1 over the square root of g over l. Okay, so we can work it through like that. Now, we can ignore the constants because we're the same value, so 2 pi makes no difference in this equation. So you work them through and you work to see which numbers give you the same value. So as a result, you do the square root of m over k and the square root of g over l. And you look at those values and which gives the same one. So if you look in there, the square root of 0.5 over 50 and the square root of 0.1 over 10 gives you the same answer, so the answer is therefore D. Now all the other values wouldn't give the same answer if you work them through. 25. A simple pendulum is released from its extreme position and completes one oscillation. Which graph shows the variation of kinetic energy with the time for the oscillation? Now, like we said before, energy is a scalar, so it can't be a negative. It can only be a positive. So C and D can't be the correct answer. Now, at maximum displacement, the kinetic energy stored is at a minimum, and the gravitational potential energy stored is at a maximum. So it says it's released from an extreme position. So at time t equals 0, it's not moving, but has maximum gravitational potential energy. So that equates to the graph of A, not B. Right, which graph shows the variation of amplitude with driving frequency f for a damped system undergoing forced oscillations? Now, the point is damping has a greater effect at higher frequencies, which causes the graph to shift towards the lower frequencies. Remember what we said before, dampening not only lowers your actual peak, it's not only spread your peak out, but it makes your peak go slightly to the left. Now, the only graph here which shows a peak slightly to the left is the B graph, indicating that is the correct answer. Right, two simple pendulums of frequency 0.5 Hz and 0.4 Hz are respectively set into simple harmonic motion simultaneously and are initially in phase. What is the minimum time to elapse before they are instantaneously in phase again? So let's follow a similar procedure like what we did before. So you find the difference in frequencies, and the difference in frequency is 0.1 Hz. Then the time interval of the frequency being back in phase is 1 over the difference in frequencies. So it's 1 over 0.1 Hz. So 1 over 0.1 is 10. The answer is C. 28. A 45-gram mass suspended from a vertical spring performs simple harmonic motion. What mass must be added to the system to double the period of oscillation? Right, so we know that T is approximately equal to 1 over the square root of m over k from what we've learned before. So therefore, T is approximately equal to 1 over square root m. This means to double the time period, you've got to quadruple the mass because the mass is being square rooted. So therefore, you've got to quadruple it to get that doubling effect. This means the overall mass to get double the period must be 45 times by 4, but just remember something, you've already got 45 grams on the actual spring. So even though you need 180 grams in total to get double the period, well, what do you need to do to get to 180? You need to add 135. So our answer is C. Next one, 29. What is the angular speed of the car wheel of diameter 0.400 meters when the speed of the car is 108 kilometers per hour? Well, the first thing you need to do is convert 108 kilometers per hour into meters per second. So it's 108 times by 10 to the 3 divided by 3,000, let's get this right, my apologies, 60 times by 60, which is 3,600. So therefore we get an answer of 30 meters per second. And therefore angular speed is going to be V over R, because we know omega is equal to V over R, as V equals R omega. So therefore we do 30 over 0.200, which is 150 radians per second. The answer is B. And finally, the last question, which of the following statements is true when an object performs simple harmonic motion about a central point O? Well, what do we always know? In simple harmonic motion, the acceleration always acts in the opposite direction to displacement. It acts towards the center of the actual oscillation. It acts towards the equilibrium position. So the acceleration will always act at the central point. It will always act towards O. So therefore, is it always directed away from O? No, it's acting towards it. The acceleration and velocity are always in opposite directions. No, that's the acceleration and the displacement. The acceleration and the displacement from O are always in the same direction. No, they're not. They're in opposites. And the graph of acceleration against displacement is a straight line. Well, yes, it would be, because you've got that constant value there, because you've always got the same force acting upon it. Right. So, with those particular questions, hopefully you can understand the different concepts of periodic motion. You can answer questions on periodic motion, and from this you can review your understanding on periodic motion and look to how to improve this further. And with that, we've finished the periodic motion course. So we've looked at circular motion, simple harmonic motion, simple harmonic systems, force vibrations, free vibrations, resonance and dampening. I hope you've enjoyed this look at periodic motion, and have a lovely day.